All right, in this work example, I'll be going through question 36. This comes from 2019 paper 11. I think this was, William, do you remember this was your suggestion? You know if this was October, November, or May, June? So this is the May, June 2019 paper 11. Question 36 reads, a cell is connected to a resistor of resistance 3 ohms. The current in the resistor is 1 amp. A second identical resistor is added in parallel. The current becomes 1.93 amps, and we're going to solve the EMF, E, and the internal resistance lowercase r of the cell. So right away, we can write V equals minus I R. Pretty laggy today. We know that we don't know the EMF, but we know when the current is 1 amp, there's a resistor of 3 sort of ohms there. It's perhaps helpful to sketch this out. And so we've got an EMF source, and we kind of think about it like there's a little internal resistor in there with it. And it's going out to a 3 ohm product. Got it like this. Okay. So we don't know what the EMF really is inside of the battery, but we could maybe calculate the terminal PD because we know that there's a 3 ohm resistor and we know that the current is 1 amp. So we can calculate the terminal PD using, Ohm's law, P equals IR. And if we multiply 3 times 1, we get 3 volts. And so the terminal PD is 3 volts for this sort of first circuit that's built there. We don't know the EMF. We know the current's 1 amp. We don't know the internal resistance. And so for a given EMF, I could tell you what the internal resistance is, or vice versa, but I don't know which set of values is correct. There's too many solutions right now, 2 unknowns I can't solve. I need another equation. Yesterday, I think where we left off was considering if we add another resistor in parallel to that one that's identical, it has the same 3 ohms. Let's calculate what the equivalent resistance of this parallel circuit is. In other words, we need to recalculate the terminal PD. Okay, the terminal PD is no longer going to be 3 volts because we're driving more current through the battery. We're going to lose more volts. Okay, we have to account for the fact that more volts are going to be lost now. So whatever the EMF is, less voltage is going to be available in the external circuit now. So we do need to recalculate the terminal PD. So here we've got a third plus a third equals 1 over the equivalent resistance of the parallel circuit. 1/3 plus 1/3 is 2/3. If 1 over R equals 2 over 3, and again, I'm expecting you to be familiar enough with, remember how we add resistors in parallel here. Like I didn't take a moment to sort of, well, I am now, I guess. Remember, we add the reciprocals of the resistance to calculate the equivalent resistance of a parallel circuit. So if 1 over R equals 2 over 3, then R equals 3 over 2, which is 1.5 ohms. So that's the new resistance in this circuit. Okay, there's 1.5 ohms of equivalent resistance in the circuit now. So we go back up to this one. We know that the current in the battery is 1.93 amps. Okay, I kind of understood that this is the total current in the circuit because we kind of know, like, well, some of that current's going to go this way. It's like half of it would go here, half of it would go here. So it's 1.93 amps sort of total. And sometimes they'll word that by saying the current in the battery or through the battery, because that's where sort of Kirchhoff's first law says the charges have met back up. And so 1.93 amps going through the battery. So it's like, well, if we know the equivalent resistance of the entire circuit is 1.5, and we know that there's 1.93 amps sort of going through the battery, then we can recalculate the terminal PD like this. Okay, give us the new current. So what's 1.93 times 1.5? Are we getting 2.895? So now we've got V equals E minus IR. So we've got 2.895 0.95 volts. That's the terminal PV for this arrangement, okay? Equals, EMF is the same. The current is 1.93 amps now, right? They tell us that. So E minus I, and we still don't know lowercase r. But what we do have now is a system of equations with two unknowns. And so when you get to algebra 2, you learn how to solve systems of equations, right? And it's never r and e, it's always x and y. And there's three ways that you probably learn how to solve that. One is we could graph them. Now, we couldn't really use that here because what we would want to plot would be like I against V, like IV characteristics, but our solutions are the EMF and the internal resistance. And so we would have to sort of create a coordinate, a set of coordinate axes of EMF and internal resistance and kind of, so graphing is one way where these are linear equations, right? They're lines. And in fact, it's a line that we're going to sketch for our lab work. Okay, like that equation is the line that sort of captures the relationship in our lab work this week. So where those two lines intersect, the coordinates are the solution. Okay, we're not going to solve it that way. The other way is substitution, right? We can solve one variable in terms of the other one and plug it in. And then elimination is the other way that they sometimes teach you. And sometimes questions are just, it's easier to solve it with elimination, the way that it's like worded. But substitution always works. It just looks a little bit sort of, more complicated when it's like, you look at two systems of equations and it's like, the x's and the y's are together on one side of the equation and equals some constant. Usually elimination works better then because x is going to be some crazy, rational function that's harder to plug in, but it will work, it'll always work. All right, so let's kind of clean this up a bit. Get all this digital ink off of my paperwork here. Oh wait, we need that one. I'm just going to leave it like this. Remember that the current here was 1. Like we got 3 volts of terminal PV when the current I was 1. So 1 times R is just R. So I got that equation, I got that equation. I'm going to rewrite it to clean it up without the units. Okay. So I've got three. How laggy it is. So I got 3 equals E minus R, right? Our first equation. We know the units are all correct to give us sort of volts and ohms out. We got the other equation, 2.895 equals E minus 1.93 R. There's a minus sign in there. All right, so 2 equations with 2 unknowns means we can solve it. Let's kind of solve this one. You might be tempted to add sort of R to both sides and say, well, E is 3 plus R. But I'd rather say that R is equal to what? So if I add R to both sides and subtract 3 from both sides, I'd have E on this side minus. I'm going to solve it for R over here. So I can plug it in. In other words, I want to know the EMF first. I don't want to solve for the R. I mean, I know R in terms of E. But when I plug this in here, right, then I've sort of substituted out this variable. So now there's only going to be this unknown. So I've got 2.895 equals minus 1.93 R, but R is minus 3. Right, and that's substitution. Substituted in E minus 3 for R. Now we distribute, right? 1.93 times E, or negative 1.93 times E is negative 1.93. Negative 1.93 times negative 3 is 5.79 plus 5.79 1E minus 1.93E plus 5.79 is equal to 2.895. Subtract 5.79 from both sides, so I got 2.895 minus 5.79 to give me, I'm going to do this also, so 1 minus 0.93 is negative 0.93 equal to, I subtracted this 5.79 from both sides to get negative 2.895, what's the same thing? Dividing that by 0.93 or negative 0.93, I get an EMF of 3.112. I always like to put the units back in when I report my final answer. At this point, there's no ambiguity. Like we could just, say, well, C has to be the right answer there. You could, if you really wanted to, plug that back in for E up here and say, oh yeah, if I take 3 away from it, that's like saying this was my EMF, but remember, how many lost volts did I have? I had 1 times 3. I had 3. I'm sorry. I had how many lost volts would be this number times the current one there. So I've lost what 0.113 volts. 0.1129. I think if we sort of plug it in. Yeah, 3.1129. So it actually does round up to 3.113. You can plug it back in and solve. And I think I mentioned yesterday that I suspected this answer initially because as soon as we kind of know that the terminal PD is 3 for that first circuit, you kind of say, well, only B or C are sensible, right? Like they're not gonna have a whole bunch of lost volts like that, like we lost a tremendous amount. I mean, this is kind of doesn't make sense. How do we draw 3 volts if we don't even have that many volts in the EMF? So like A is clearly wrong. But because it is wrong, but I see the same numbers here, it makes me feel like that's the correct answer. That students that mix something up with like R and the EMF might like get these values interchanged. Like they did the correct calculations, but maybe they just sort of mixed up what was what, and so they incorrectly choose this. And so without really knowing much physics, you can just be a really astute test taker. And I would say it's maybe not so much astute, but like a risk taker. It's really risky to say, I think it's C just because these numbers are the same, and I feel better about this being the EMF based on a little bit of physics, like V equals IR, 1 times 3 is 3 volts, that's the terminal PD, and the EMF can be a little bit bigger. And so you'd say, well, it's either this one or this one, and I don't like this answer because seeing the same numbers here makes me feel like that answer was included to capture the students that like made some mistake. And so, like you could reasonably calculate these values because they are the correct answer, but it's just like that's the EMF and that's the internal resistance, right? And so it's really risky to just sort of rely on that sort of, oh, my test taking, sort of strategy tells me it should be the best answer. And you avoid all of this, physics and other stuff I erased. But it's not too bad once you have the way to solve it in mind. And I think as soon as like class was dismissed, I think Krista suggested something that was like, oh, okay, I think you're onto something with that. I was like, oh yeah, system of equations, right? And I think we were even starting to sort of approach that. We were just considering, oh no, the V is going to be different, right? Like we can't just say that we're still going to have 3 volts of terminal PD when we add the second resistor. We had to calculate actually like what the terminal PD. We were sort of the bell rang before we did that. Question, William, you had a question? Yeah. Yep. You're saying after the first one, or once we've calculated the total. We got this equation. And just try them out, plugged in. Well, let's test and see that these quantities work. Because if they do, then no is the answer to your question, right? Like, because then the wrong answer sort of gets you there. And so it could be true, true that that's the case. And so let's try 1.93 times 0.0358, and that gives us 0.069. And if we did 3.04 minus that to make that negative, and then add the EMF they suggest, you get 2.97, which is not 2.895. And so, yeah, you would say, oh, no, that one doesn't work. Doesn't give me the 2.895, I suspect. And so only this answer would work. So, yeah, once you kind of get it down to where it's very manageable, then you can just like test some values. And really with multiple choice tests, there's always a sort of inefficient strategy at your disposal of testing everything out until you sort of find one that works. And hopefully it's A when you have to sort of go to that. It's like, well, I'll just do them in order, A, B, C, D, and hopefully it's not B. Because that's like all that work there for finally. Any questions on this one? All right, let me go ahead and be mindful to stop the recording.